The objective of this video is to introduce the 3-terminal linear regulator for power control. We're going to do this by considering the single-phase low-frequency rectifier that we've been developing over the past few videos. And when we first started considering this circuit, we decided to model the output stage as a fixed DC voltage source. That is, we modeled the resistor and capacitor as a voltage source equal to VDC. And we've seen as we've developed this circuit that that is not true. In fact, our output voltage will fluctuate as our capacitor charges and discharges, and may look something like this. Now, these fluctuations can cause problems for digital circuits. So a waveform that has this pattern, where our output fluctuation is sizable, is really not very useful to us in most applications. About the only thing that it could be useful for is driving current through a resistor, perhaps as a heating source, or maybe as a light bulb as a source of light. But if we're trying to provide a power rail for USB or a microcontroller, this is simply unacceptable. When you want to design a DC voltage supply, you have to be sure to pay attention to the design spec for the system that you're driving. So if you're trying to drive a microcontroller, you can pull up the datasheet and figure out how much ripple voltage is allowable on the voltage rail. For most real loads, we want to have a regulated DC voltage. And we're going to spend a lot of time in this class talking about ways to convert one DC voltage to another DC voltage efficiently and in a compact form factor. Today we're going to introduce our first approach to this, and we're going to motivate this based off of the voltage divider circuit. Suppose that you attach the following circuit to the output stage of your diode rectifier system. You can see that you can select the values of R1 and R2 to give you a different voltage value. So if your input voltage is 10 volts, for example, you could pick R1 and R2 to give you a voltage output of 8 volts. Unfortunately, this voltage is going to change as your load current changes. So, as drawn right here, it's not very useful for regulating the voltage, but it offers us a way to step down the voltage input. If we want to regulate the voltage, we need a circuit that looks something like this. In this circuit, we acknowledge that we have a variable input voltage on the left side, and we connect it to our voltage divider network again, but this time we're acknowledging that R1 is a variable resistor. In fact, I'm going to term this as a transfer resistor. Transfer resistor because we're able to electrically control the value of the resistor. If we can control the value of this resistor, we can change the mapping of our V out regulated to our V input. And the question now that I want to pose to you is, does such a device exist? Is there such a device that we can electrically control the resistance of? And in fact, such a device does exist. It's called a transistor. The word transistor is coined from this phrase, transfer resistor. So let's redraw this now in a way that represents what an actual linear regulator looks like. So in this case, you see that I've replaced our variable resistor with the transfer resistor, with the transistor. And inside here, I'm going to connect a feedback network. So you see that this feedback network is measuring the value of our output voltage, multiplying it by a gain, and feeding that into an amplifier, into an op-amp. And that amplifier is used to drive a current into the base of the transistor to change its resistance value. So this circuit should be familiar to you. It's the classic emitter-follower circuit, which you learned about in ECE 342. We can bundle these elements together into this blue box, which is the physical linear regulator device. So everything in this blue box is sold to you as a single integrated circuit that you can buy off of DigiKey, for example. So I'll redraw this yet again to represent the block diagram of how you'd use such a linear regulator. And you can see that we have literally replaced that blue dash box with this black box. I'm going to highlight on the blue dash box the terminal connections. You have a connection right here to your input voltage, you have a connection to the common of your signal, and you have a connection to your output voltage. When you go purchase a linear regulator, You have to determine the power rating that you need to operate at and the output voltage that you desire. A few key points about these systems. They have low efficiency. So if you were to use these to convert over a very large voltage range, you'll see that you have extremely poor efficiency. For example, if you're going from 200 volts input to 5 volt output, you'd have only 2.5% efficiency. And you can calculate this for yourself. If you take one of our early voltage divider circuit, you put 200 volts in the input, you can figure out the resistor values that you need to obtain a 5 volt output. And you can see that you only have 2.5% efficiency if you do the calculations. So for this reason, these things develop a lot of heat. And we can see that they're only going to be useful for low voltage range conversions, so converting between a rather small difference in voltages, and for very low power levels. The final point I want to make is that this system leverages feedback control and voltage regulators, which is more complex. So the linear regulators provide us a way to very precisely regulate voltage. They can be used to step voltage down, and they can be used to obtain very precise regulation. Over the next couple of months, we are going to be looking at a completely different method for realizing power electronics and converting between voltage levels. This is called switched mode electronics, and it allows for very efficient and compact energy conversion. It is oftentimes used in conjunction with linear regulators when precise voltage regulation is required. We'll be starting this lecture series in our next video.